Before we start talking about dynamics in this class, I need to talk about a few mathematical preliminaries, mathematical things that are going to come up over and over again, that when you learned them in the class that you took in calculus or whatever, they may have sort of flown by quickly, but in this class, it turns out they're going to be sort of cornerstone things. So I want to make sure that you understand these completely. So I'm going to start out by talking about ordinary differential equations. I'm always going to abbreviate that as ODEs. That's a pretty common abbreviation. And there's really going to be, if you take Calculus 4 differential equations, there are a whole bunch of techniques for solving these depending on what the ordinary differential equation looks like. In this class, there's only one that you're going to be responsible for. And in general, this is the one that's the most useful in future classes and things. It's called separation of variables. So I'm going to first talk generally about ordinary differential equations. Then I'm going to talk about how to solve certain ones using separation of variables. And I'm going to abbreviate this SOV. The next topic, and by the way, this first one is going to be by far the longest of all of these, because this is, a complicated topic, differential equations. Then after we're done talking about ODEs and separation of variables, I'm going to talk about derivatives of vectors. In calculus, a lot of times you don't think of it as derivatives of vectors, but I just want to make sure that we're all on the same page with this, because many of the quantities we're going to be dealing with are vector quantities: position, velocity, acceleration, force, lots of things. Next is the product rule. And then the last one is the chain rule. So this first one is differential equations. You can group these three together as things that are going to be important for functions of one variable. We'll see as we go on and talk about ordinary differential equations that ODEs is actually a topic dealing with functions of one variable too. So that's going to be something common in this class. We're usually going to have one independent variable that we're dealing with. And in dynamics, that's generally going to be time, t. Okay, so the first topic is ODEs. And when you see an ordinary differential equation, there are three things you need to identify before you can go on any further. So you must know three things before you can solve a differential equation. The first one is you have to know the independent variable or independent variables. If you have one independent variable, which is what we're always going to have in this class, then you have an ordinary differential equation. So that's what we're going to be dealing with. If you have more than one independent variable, then you have a partial differential equation. Or what's referred to as a PDE. As you might imagine, those are much more difficult to solve. And if you haven't seen these in a class yet, you'll most likely eventually have to take a class in PDEs. But PDEs are so hard to solve. Generally, you just go right to a numerical solution, except in a PDEs class. Okay, so first you have to identify what the independent variable or variables are. Next, you have to identify the dependent variables. And these dependent variables are always functions of the independent variables. So for example, if your dependent variable is x, then, and your independent variable is t, then what you're trying to solve for the differential equation is the function x of t. Unlike the independent variables, something isn't an ODE or a PDE based on the number of dependent variables. So you could have an ODE that you're solving for 3 or more different dependent variables, 3 or more different functions, okay? The only thing that defines ODE versus PDE is the number of independent variables. And one more thing about this. The dependent variables are what you're trying to find. That's what you're trying to solve for. You're trying to find this function or these functions of the independent variable. And then the last thing you need to know before you can start to approach trying to solve a differential equation is you need to know how many boundary conditions are needed to solve your differential equations. And of course, you need to know, so however many boundary conditions you need to know whether you have them or not. A boundary condition is a value of the dependent variable at a specific independent variable value. So for example, if your independent variable is time t, your dependent variable, say, is x, then an example of a boundary condition would be at time equals 0, x is equal to 5, okay? It's a relationship between a value for the independent variable and a value for the dependent variable. Since we're only going to be dealing with ODEs, we don't have to talk about boundary conditions for PDEs. As you might imagine, they're much more complicated. But for ODEs, for each ordinary differential equation, you need a number of boundary conditions equal to the order of the differential equation. Okay, so if you have a single differential equation and the highest derivative is second, that's a second order differential equation, then you need one boundary condition for each order, so you need 2 boundary conditions. Okay, if you have a system of differential equations where one is a first order differential equation and one is a second, then you need 1 boundary condition for the first order plus 2 boundary conditions for the second order, so you need a total of 3 boundary conditions. Okay, so let's go through a few examples of ordinary differential equations. And hopefully this will, help you get straight what what kind of answers, these three things that I talked about, what do they look like for a specific problem. So, okay, let's say the first differential equation is dx dt is equal to 5tx plus t squared, where the x value when time is equal to 0 is 4. Okay? And let's just go through that list of things that we need to know. Okay, so first, what's the independent variable? Well, there are two things that you can look for here. First, look for what you're taking a derivative with respect to. That's going to give you the independent variable. Also, if your derivatives are complete derivatives as opposed to partial derivatives, that tells you that there's only one independent variable. So in this case, the independent variable is t. There's only one of them, so this is an ODE. Okay, and this is the case that we're going to have almost all the time in this class. We're going to have an ODE, and the independent variable is going to be time. Second, dependent variables. Well, there's only one other variable in here, and that's x. And so what we're looking for is x as a function of time. Okay, so we will have solved this problem when we have a function x depending on t. So, for example, maybe you'd have a function x of t where that x is equal to 5t squared or something. Then you've solved this problem. Okay, how many boundary conditions do we need, and do we have them? Well, this equation, we have one equation, and the order is first, right? There's only a first order derivative. So we need one, and do we have it? Yes, we have one value of time where we know the dependent variable value. That's the x of 0 is equal to 4. So if you have the boundary conditions you need, you can solve this. If you don't, you can't solve it. So this tells us that we can proceed and try to solve this differential equation now. That doesn't mean we're going to be able to solve it, but it means that we can at least start to approach solving it. Here's a second example. 10 dx dt plus 50t is equal to 0, and dy dt minus 10y t squared is equal to cosine of t. Where y of -2 is equal to 10. Okay, so first, the independent variables. The only derivatives we have are with respect to time, and they're complete derivatives. So the only independent variable is time, and that means this is an ODE. So that's good news for us. Second, the dependent variables. What are the variables that we're taking derivatives of with respect to time? We have a derivative of x with respect to time and a derivative of y with respect to time. So we're trying to solve for two functions, x of t and y of t. And finally, we have to figure out how many boundary conditions we need. Um, so this is a system of two equations. Each one is first order. So we need one boundary condition for the first equation plus one boundary condition for the second equation. So we need two. And now we look back at what we're given for boundary conditions, and we have one place where we know the value of a dependent variable at a given p-value, but that's not enough. So we don't have enough boundary conditions. And what that says is we can't solve this. We're not given enough information to solve this differential equation. For the people taking differential equations, sometimes you're asked to give solutions to things where they don't give any boundary conditions, and that can be a little confusing when you compare it to what I'm saying here. Well, you can give what's known as a general solution, where you put in constants, essentially constants of integration, and those are arbitrary values that can be anything. And then when you're given boundary conditions to meet those constants, then you can put a specific function to it. But for this class, if you don't have those boundary conditions, we're not going to do anything with general solutions. And so, so if you don't have the boundary conditions, you just can't solve it, and that's the end of it. Okay, here's a third example. 2 partial of z with respect to x plus 3 partial of z with respect to y is equal to 10xy. So independent variables, well, we have partial derivatives, so that says that we're going to have more than one independent variable, most likely, although that's not necessarily the case, but that's an indication that to look for this to be a partial differential equation. And the derivatives are with respect to x and y. And we don't have, any other variable that x and y are derivatives with respect to. So the independent variables are x and y, and that says that this is a PDE, partial differential equation. Okay, well, so for all intents and purposes, in this class, for sure, we're done. I mean, there's nothing we're going to do with that in this class. But if you were in a class where you had to solve these PDEs, then you'd have to identify the dependent variable or dependent variables. In this case, you have one dependent variable, and that's z, which is a function of both x and y. And then the boundary conditions, that gets more complicated for PDEs than it was for ODEs, so that doesn't really concern us. Okay, here's a fourth example. And I'm going to give this one in the form of a vector equation. So say that you have x dot y dot is equal to the matrix 10, 0, 0, negative 5 times xy plus the vector 10 cosine of the quantity 3t, and then the y component negative sine t. And say that we're told x for time equals 0 is equal to 20, and y for time equals 0 is equal to 0. Okay, so let's identify these. So the independent variables. Oh, and first, this is a notation that probably a lot of you have seen. Maybe some of you haven't, or you don't remember what it means. But this dot notation, when you see a dot, that means a complete derivative of the variable with respect to time. So this is the equivalent of saying the derivative of x with respect to time is equal to, and the y component says the derivative of y with respect to time. So for the independent variable, again, we're taking complete derivatives with respect to time. So our independent variable is t, and that says that this is an ODE. And so again, in this class, so far so good is kind of the take-home message there. We can deal with ODEs, we can't deal with PDEs. So as of now, we're still on track to be able to solve this problem. Second, the dependent variables. Well, we're taking derivatives of x and y with respect to time. So the dependent variables are x of t and y of t. So those are the two functions that we're trying to solve for. Then the third one for the boundary conditions. This might be, for this one, it might be worth rewriting this in a new form. So this vector form is equivalent to this. You can rewrite it as dx dt is equal to 10x by the rules of matrix multiplication plus 10 cosine of 3t. And the second equation is dy dt is equal to negative 5y minus sine of t. And we still have those two boundary conditions, so we know that x when time is equal to 0 is 20, and y when time is equal to 0 is 0. Okay, so now let's think about the boundary conditions. We have a first order differential equation here, plus a first order differential equation here. That's a total of two boundary conditions that we need. And we're given these two boundary conditions. And that tells us that we still believe, after going through this first analysis, that we might be able to solve this problem. Okay? Okay, so let me give you a couple of kind of take-home message type things that you should remember. First, with an ODE, you're trying to calculate functions of a single independent variable. Second, how many boundary conditions do you need? Well, if you have a single nth order ordinary differential equation, you need n boundary conditions. If you have instead m nth order ODEs, that tells us we need m times n boundary conditions. And you can go on to more complicated combinations of these, but that's the idea when you're looking for how many boundary conditions you need. And in this class, we're going to be always dealing with ODEs with time as the independent variable. Okay, so the next lecture I'll give you will talk about the technique, the only technique that we're going to need to solve these differential equations, and then after that I'll go into the other mathematical preliminaries.